Alright, let's review some basic nomenclature regarding reactions. And so we're going to consider the following reaction that involves methane and water reacting to form carbon monoxide and hydrogen. Okay? On the left side of the reaction equation are your reactants. On the right side are the products. And we're going to refer to methane as chemical A, water as chemical B, carbon monoxide as chemical C, and the H2 as chemical D. All right? And so in front of H2, you see that, there's a 3 there. We're going to refer to that as the stoichiometric coefficient to H2. Okay? So anytime you see a new sub I or any of the coefficients that are in front of the chemicals, we call those the stoichiometric coefficient. And in general, we define them as being positive for products. So for H2 here, this would be a positive 3. And we would define them as negative for reactants. And so for methane and H2O here, they also have stoichiometric coefficients, but their stoichiometric coefficients would both be -1. And of course, if there's anything else in the system that actually doesn't participate in the reaction, but is in the feedstock, so something that's like a catalyst or an inert, their stoichiometric coefficients would be 0. So these are, basically additives that maybe can help control the rate of the reaction, but don't necessarily participate in the chemical mechanism themselves, or at least explicitly. Okay, all right, and so, when we define a stoichiometric coefficient, we could take a chemical reaction like this, and we could write it in a more mathematical way, like this. So I can write chemical reactions in this format, where we basically just write the reaction as a sum of the stoichiometric coefficient times A, B, so on and so forth. So basically what we have is the sum for however many components we have in the reaction of nu I and then chemical name sub I. Okay? Now, in general, if we want to consider the change in moles of each of the species, we would say that the change in moles for a particular species I divided by its stoichiometric coefficient, that ratio should be the same for every species participating in the reaction. Should be the same for each species. Okay? So for instance, if we wrote that the change in moles of species A divided by the stoichiometric coefficient of species A, that would be the same for dNB over nu B, which should be the same as dNC over nu C, which should be the same as dND nu D. Alright, and so all these ratios should be the same. And all the ratios are the same, and they're going to be equal to what we call the derivative of the extent of reaction, which is this epsilon symbol here. Okay? And so this is called the extent of reaction. And the way to think about the extent of reaction is it's just kind of like a fancy way of saying the number of times a reaction occurs. Okay? So, for instance, let's say you ran a reaction that produced 1 mole of carbon monoxide and then you did a separate reaction which produced 2 moles of carbon monoxide, right? You would say that that second reaction had a extent of reaction that was twice as large as the first reaction because you were able to produce more product. So in any case, the extent of reaction, just think of it as the number of times a reaction occurs. Now that we define the extent of reaction, we could sort of rearrange it in this way, such that we could say that the change in moles of species I is just going to be equal to the stoichiometric coefficient times that d extent of reaction. Okay? And so the nice thing about this is that this extent of reaction is just a single variable, but we can use it to describe the change in moles for all the species involved in the reaction. Describe changes in moles for all species. And so we have dni is equal to nu sub I d epsilon. And of course I wrote this in derivative format, so what we could do is we could just integrate it, and we get ni is equal to the initial amount of moles of species I plus nu I epsilon. Okay. All right. The last thing I'll say is, I wrote out this sort of equation for just talking about a single reaction. But a lot of times in real actual chemical reactors or in real chemical reactions, there's not just one reaction going on. You actually have to account for a lot of side reactions, or there's multiple reactions going on. And so if you're dealing with multiple reactions, then each reaction you're dealing with, or each reaction J, is going to have its own extent of reaction, so its own epsilon sub J. And so for each species in the system, not just in each reaction, but for each species in the system, you would say that the number of moles species I is going to be equal to Ni initial, or Ni naught, plus the sum of J is equal to 1 for the number of reactions in the system, nu ij, so this is saying that, species I can participate in J number of reactions, d epsilon J. Okay? And so that's how you would write this reaction, or this equation, if you were dealing with multiple reactions.